Okay, in this video we are going to have a look at the tools that are commonly applied to the identification of minerals. The tools are used to identify the properties of minerals, and mostly, most of the tools are used for hardness. So if we start to look at them, we have already discussed and introduced the tools, but here it's worth having a recap and sort of looking at them. So I will use a pen just to illustrate things. Here we have the copper coin. This is the pin nail, the knife, the magnet, a ceramic plate, a glass plate. This is a hand lens, and that's our hydrochloric acid at 10% in this case. The other tools that I have, it's usually my thumbnail, so I can use it to scratch a mineral. So we could take an example here. I can test, try to scratch the faces of this crystal and see that it doesn't really work. I cannot, in this case, scratch it. So this is how you do it. You try to scratch the surface. So that's the softest, the fingernail, it's on the order of 2 to 2.5, and then you go up in terms of strength. So the magnet is not used for hardness. We usually have that the first tool after the fingernails is the copper coin. Then we have the pin nail, the knife, and then we have, I think, the glass and ceramic plate. So the glass will be on the order of 5.5, and the ceramic plate or strict plate is up to 7, so 6.5 to 7. So for the first three, you usually pick up these and try to scratch. So we grab another mineral here. We will discuss the minerals later, so I'm not going to tell you what this is. It's just to show you that I can take this copper coin, which you will have likely, and I can try to scratch the mineral. And in this case, it's not really working. See, I am actually ruining the coin. So why is that? Well, that's because the hardness of this mineral is either harder or the same. So do you think that this is harder? Well, we don't know until we test it. So if we use a pin nail, it's on the order of 4, and so if I'm able to scratch the mineral, and so you can see here clearly some scratches, I would automatically know that this mineral has a hardness that is less than 4 and probably on the order of 3. So this is how you test for hardness. Of course, it would be even easier to use, a knife, which is 5.5 to 6, and I can see even sort of more pronounced scratch on this fairly polished surface of this mineral, which I can tell you it's actually calcite. And so calcite is the mineral has hardness of 3. Okay, so what if I take the knife and I take another mineral, so this mineral here, which is somewhat similar in color, I can see that not even the knife can actually scratch this mineral. So it's quite hard, and it does even scratch glass. So if I use it like this, you can see the scratch quite well in this glass plate. So this is how you use the glass plate. It is actually important to realize that the scratch can be either on the mineral or on the tool, depending on the type of tool you are using. So if we use these plates, we look for scratches on the plate. This is the ceramic plate. You can try to scratch the ceramic plate and see if effectively it does leave a mark, and you can see I don't really see a mark left on this ceramic plate, which means that the mineral, is not as strong as the ceramic plate. So in this example, we are talking about a mineral called quartz. So it's essentially silica. It does have the same composition of this glass, but the structure is different. So this is ordered, this is unordered or amorph, and that's why you have a difference in hardness. This is far harder, and it's around 7, which is again part of the Moss scale. And so we have reviewed the main tools for testing for hardness. In the next experiment, we are going to review these other tools, which are again the acid, the magnet, and also the end lens. So the end lens is the easiest, is the first really, and we could make an example with this mineral here. Sometimes you need to look at sort of enlarged versions of the mineral, and what we are going to do is to look at some of the features of minerals with some magnification. So keep in mind that as part of this mineral kit I recommended, there is a hand lens, and you can use it to evaluate things. For example, cleavage on a mineral. So we have looked at cleavage like this beautiful example of feldspar, which is, as I stated during the lecture, this set of repeated planes that you can find in minerals. So in this case we have here one plane, and you can recognize another one that is parallel, and then another one here. So we have at least 3 planes that go across this mineral, and that is commonly a good definition for cleavage. So the fact that you can recognize planar surfaces that are all parallel to each other will be a good diagnostic criteria. But in some cases the minerals will be relatively devoid of this fracturing, and so you can look at microfractures using a hand lens like this one here. Other things, yes, the magnet. So many times we will find minerals that are not very transparent. They look dull or sometimes metallic, like this example here. Well, these are sulfides and also oxides, and it happens to be that you can test for magnetic properties like this. So this example likely contains pyrrhotite. So if you have pyrrhotite veins, they will be magnetic. Okay, so you have to record this information, so be able to recognize weakly magnetic like this example here, or highly magnetic like magnetite. We can look at another specimen, I think. Okay, we were reviewing the end lens, the acid, and also this one, so the magnet. So the end lens is, as I stated, for the feldspar, a magnification factor that can help you with the identification of features like cleavage. We have other minerals like oxides, and I have an example here, and also sulfides that quite often will be attracted by the magnet. So how do you apply this magnet? You simply attach it to the surface and check, that the magnet sticks to your mineral. And so that's all. It's not very difficult to do. You just look at things like this, or you could put it on a table and see whether it sticks like this. So this is not the only. So magnetite is the #1 candidate, but then you have circumstances like this in which you have a sulfide. In this case, if you look carefully, you can see this goldish mineral, but which is your pyrote, or some cases it's more orange like, so darker gold, and that will be your chalcopyrite, so a copper iron sulfide. And then we have other copper iron sulfides that are more bronze in color, and these are your pyrrhotite. And pyrrhotite is partly magnetic, it's weakly magnetic, so you can test for that in pretty much the same fashion. You will realize that the magnet doesn't stick as well, but it does still stick. In fact, we have other tools that commonly are used by geoscientists, especially when they do mineral exploration, really like this pen here, which is magnetic on its tip, and so you can test weakly magnetic things if the pen moves, basically, and you can see that it moves quite a bit. So weakly magnetic minerals like that can be tested, and you can see that it does move still, because of course this mineral contains also chunks of these other mineral, which is pyrrhotite. So sometimes you will find 2 or 3 minerals. I recommend that during your examination you discuss the main one, but since we are doing oral examination this year, it's going to be easy. I will tell you what I'd like to know about a specific specimen. But that's how you test for magnetic properties. So if you take the magnetite here, see how much more intense is the response, and of course that is quite evident and will help you with the recognition of these minerals. One thing I was really forgetting, I think, is the fact that the streak plate is not only used for the identification of hardness, we also use it for testing for streak color. So like in this case, if you have a magnetite, the streak color should be very dark, and in fact it is. You can see clearly that the streak is black in this particular case. This is quite useful, because if we take another mineral like this one, which doesn't, it's kind of similar, so still very massive, but more, you can see a little bit more reddish, but sometimes can be very dark like that, like this example. I think now this is the magnetite, but yeah, there will be cases in which the color is not very helpful. Okay, so the color on the surface, because of the oxidation, can be difficult to tell sometimes. And so what we do is to test for the streak. And so if you use the streak color, you can see clearly the difference here. And so this is more brown to reddish, this is black. And so that's your magnetite, and this is your hematite. And that's another example how we do investigate the streak color. You can take also sulfide, and this should be black as well. And you can see it's clearly black, so that's a good diagnostic analysis of sulfides when you're looking for pyrote. Yes, so in this case the magnet will tell you the same thing, because it doesn't really stick, or if we use my more sort of sophisticated magnet. If it's completely steel, we can sort of experiment and see that it doesn't really stick at all. It doesn't move my pen much. Okay, so the hinge is not really responding. It might be that you have some response. Remember that sometimes you have combinations of minerals, so try to be sort of objective. But of course, for this oral examination, we'll be there, so we'll be able to help you with some of these challenges for sure. We are left with the last tool. So if we place things back and clean the space for the next experiment, I think we can take this example here, which is a crystal of calcite. You can easily recognize the shape of the crystal. In this case, it's a rhomboedral crystal. So it's like a cube that has been sheared. And so you see that the faces are slightly offset. That's a diagnostic feature for calcite. Then you have the hardness again, as we already discussed, because we had a calcite crystal that also could be scratched with the pin nail. So we could scratch it, so we could demonstrate that the hardness is on the order of 3. But another test you can do, so we could compare, quartz and also this other mineral, and which is fluorite and calcite. They are all very similar, but they do respond differently to your acid. So the calcite will actually react with acid. Hopefully you can view that, but if I put some acid, you can see a vivid effervescence, and it can fizz. Maybe the camera will be able to capture the fizzing. So really vivid fizzing with a drop of this acid tells you that this is a calcium carbonate. So that's a diagnostic criteria for the identification of carbonate. Okay, so the same should be true if this other crystal is calcite, so we can test that too, and we will see that we have a very similar effervescence. Of course, you have to be careful, do not touch acid with your fingers, but yeah, it's pretty reactive, and this is a reaction. So the bubbles you see are essentially liberation of CO2, so you get essentially a separation of calcium from the CO2 group, and you get liberation of CO2 as a gas, and that's explaining why you get those bubbles when you have so you need carbon basically to react with the HCl. Of course, if you don't have carbon, like in this case of silica, so this is an oxide of silica, you don't get really any reaction. So you see, I don't see any fizzing, not much really happening in terms of this mass of quartz. It doesn't really react very much. And then you have this one here, which is usually also not really responsive, because this is a salt, so it's a ionic compound, so it's essentially composed of fluorium and calcium, but it doesn't really give you any fizzing at all. So there is calcium in here, but it's a fluorium compound, so calcium fluoride will not really react, so you need the CO2 of your carbonates to react and do effervescence. There will be exceptions also for these guys here. There are minerals called dolomites that have a similar composition, but they will react only if pulverized and heated up before interaction with the hydrochloric acid. So also this acid will be helpful for distinguishing between dolomites and calcite, but this is sort of more of an advanced thing. So how do you tell this is, you know, fluorite and this is quartz? Of course, you would have to test with the knife and see if you can scratch this mineral, and you can see clearly I've sort of have clear scratches coming out of my interaction. So lots of scratches, or on this face, maybe you can see it. I can clearly scratch this mineral. I think that I could not really do with this other piece of quartz. I cannot really scratch it at all, so I don't see any scratches, and that's a diagnostic feature for distinguishing between quartz and fluorite. Also, the color of fluorite is quite characteristic. So many times they say it's, you know, it does have this greenish translucency. We'll see some of these more in detail later. So I think this concludes this session on the tools. In the next session, we are going to discuss other things which are more related to distinguishing the individual minerals, and we will revise, I think, some of those properties of minerals and try to use them to form groups and sort of discuss other key tips for the identification really of specific minerals as stated. So we will review some of the things we have already discussed, but these were more in the context of how you use the tools. So remember, we test for hardness, streak color. We also use magnification to identify characteristic features like cleavage, and also we test for magnetic properties and chemical reactivity to acid, and these will be all tools that can be useful. When we do the examination, I will have I will help you by telling you what is the response to a specific tool. So you can ask me if the pin nail, for example, scratches the mineral or not, and I will tell you if that's the case or not, and so you will be able to recognize the minerals. So of course there will be more emphasis on the identification of minerals, and you will have to discuss some of the characteristics of the minerals with me. So I leave you to the next video. Again, this video will be more about the different minerals that we are going to learn and their context, I think. So we will also look at the Bowen sequence again, and so think about the Bowen sequence and what minerals are part of the sequence, which are actually the most important one for the classification of igneous rocks, certainly, but also some of the sedimentary rocks. Okay, now that we completed the tools, we're going to have sort of a look at the minerals that we are going to work with, and so the exercise really will be to work through a series of minerals and try to group them. So I'm going to move some of these minerals. So you have here pretty much all the minerals I'm considering for this course, and we are going to go through most of them and attempt there are the identification and discuss some of the features that are characteristics of really all these different minerals. This is a challenging job, so we are going to try to adopt an approach that is like a divide and conquer approach, which is what I recommend quite often when dealing with large amounts of specimens. So I've got pretty much all my minerals in here. I think I probably didn't, maybe I forgot some, but yes, you can see. I think for the examination we are going to look at photographs of these minerals really and talk about them. So that is likely to happen, so you will be tested on one of these specimens likely. So the first thing really is to look at how the optical appearance is really for some of these minerals, and the first distinction I would make is certainly based on the translucency of the minerals. So what do I mean by translucency? I can take, for example, this piece of quartz. We have discussed it previously, and I can see essentially light that can go through the crystal. So if you see here clearly, I can see light going through it, and so it's essentially transparent or translucent. So that's one key property. Translucency will help you identify silicates. Many of the silicates will be translucent. Of course, this property can be variable, so some minerals will be highly translucent, and this is not a silicate, but you can see clearly that is highly transparent, and I think that's important as well. So translucency is not exclusive of silicates, but many silicates and sulfates and halides will be transparent. So this other mineral is quite transparent. So you can start by grouping minerals that are transparent and putting them here, and sort of you already have identified an important property of minerals that is common to them. And so other examples, these are less translucent really. I don't see a lot of translucency, but still I can see through the crystal, and that's important to know. So that would help me really putting these minerals in here with this group. Other minerals will be translucent but will have a different color, and this is a good example here, which I believe it's carbonate. So the color is not really a diagnostic criteria for minerals, but in some cases it can be helpful, and for example for the K feldspar it's quite helpful, but you have to be careful. So sometimes the acid can help you in essentially differentiating between carbonates that are pinkish in color, like this example here, which fizzes quite heavily, and this other feldspar which should not fizz that much, and in fact it doesn't, because this is a carbonate and this is K feldspar, and so this is a silicate. It's translucent, so it can go here as well, but it's less translucent if compared to quartz, and the carbonate could go here as well because it's still translucent. So what are the minerals that are not really translucent? Well, this is still quartz, so it goes with the translucent, but I would definitely say these minerals here. So see, this one has more of a metallic appearance, And so when they're metallic like this, so they look like a piece of lead or a metal. So a piece of lead would be something like this, which is also quite heavy. Yeah, this mineral, you can see it's kind of silvery, and it shines quite a bit. And so that's a characteristic diagnostic feature of either an oxide or a sulfide. So we have an oxide here, iron oxide, and this is a lead sulfide. And so you have magnetite and galena, and definitely you don't see any translucency. Actually, the light gets completely reflected off the face of this mineral. You can see that it shines quite a bit. And this is really important because these are called opaque minerals, and they will be quite commonly grouped together because of this property. So we could put them here, and also these others, so the hematite. So we have here bands of hematite and likely magnetite, and this is magnetite. So magnetite, hematite, galena will go in this group of the opaque minerals. And also this other mineral here, which is your pyrrhotite. So you can see it's more bronze-like in color, and also pyrrhotite will go with this mineral as well, which is this one here. So you can see the difference here. This is more, like coppery in color, and also the difference. Remember, with the magnet, you can attach a magnet quite easily to pyrrhotite, but instead here it's a little bit harder. We have some pyrrhotite in here, which can be misleading, but if you really select portions of this crystal that don't have pyrrhotite, it doesn't stick really. So you can see it's actually slipping through. In this one, it sticks quite easily. So that's mostly pyrrhotite, that's mostly pyrrhotite, and a little bit of chalcopyrrhotite in this particular specimen. Okay, so these are also opaque minerals. So we have formed this other group. These can be also quite metallic in appearance, see? And also this one here, but I would leave them as a separate group because these are silicates, and you will recognize them because of the single cleavage that they have. So if you look carefully at this specimen, you can see a lot of strata. And if you remember from the lectures, I've mentioned two important things. One is these hexagonal faces. So you can see a plug that is pseudo-hexagonal here. So we have 1, 2, 3, 4, 5, and 6 faces roughly, although there is a little bit of an overgrowth here. But yeah, it's important to recognize that this is, quite could be metallic in appearance, but is quite stratified. You can recognize a structure that is formed by a series of planes, and I can definitely see several lines in here which are evident in all faces, which suggests that you have multiple layers, and this should tell you based on the lecture straight away that this is one of those phyllosilicates that we mentioned. So either the muscovite, the chlorite, the biotite, and so we will look at these, try to identify what they are more carefully. This is the same, so they kind of are quite shiny, but if you look carefully you can see some light going through some of these crystals, and in fact if you break them quite often, we can see, like in this example here, some of these lamellae or detached planes, really, which are detached along the cleavage surfaces, will be quite transparent actually. So this is, it does have a good reflectivity, but it's more, you know, translucent because of this transparency. That's an important property, and also it's quite flexible. You can flex these quite a bit. They flex, and that's also another good indication that you're dealing with the phyllosilicate. So this is an opaque one. It will go in this group and has a similar color, so either magnetite or hematite. Remember, we can use the strict color to check. Then we have other silicates like these that are quite dark in color. You can still see a little bit of translucency, but they are really at the bottom, I think, of that group in terms of translucency, but they are silicates. So I would put them here and sort of form a group that is represented by mostly pyroxene and amphibole, I would say. So the ferromagnesium silicates, if you remember from the lecture, which would be relatively dark in color, and so yeah, sometimes they're dark greenish like these examples here, but yeah, they are sort of like a middle way between those really opaque minerals and those really transparent minerals. And so we have here your amphibole and pyroxene, same story here. You can see these large crystals. If you remember the lozenges, a good indication of that you're dealing with amphibole. And yes, these are really examples of amphibole and pyroxene, and this is also another pyroxene, and it should sit in this group of ferromagnesium silicates. This is quite dark, and it's actually a spinel, so spinel. Spinel will be a relatively hard mineral, and quite often could be closer to these opaque minerals, although it's somewhat, it can be like, it depends really on the composition of the spinel. Some spinels will be very translucent, but this example here is not really translucent, so I would place it in here. The same symmetry also occurs for magnetite, so there is actually a transition, I would say, between a variety of spinels. We have seen that they can form sort of solid solutions, and so you have substitutions that go into the structure of the spinel that will change some of the optical properties of the mineral. But certainly this is quite diagnostic for spinel, the fact that you can see a pyramid on the crystal. You can see the faces forming a pointy habit, and so I can see definitely here a pyramid, and sometimes you can recognize that this is an octahedron. So if it does look like an octahedron, so it does have like a base of the pyramid, it is a square base, which I can see it because I have a 90-degree angle here. So let's get a pen to just illustrate this feature. So you can see this dark crystal is quite shiny, and I can see here roughly an edge of the crystal and also another edge here, and it forms 90 degrees. So I hope I convinced you. And yeah, if I rotate this crystal, I also find a characteristic dihedral angle, so an angle between two faces, and in this case this angle is slightly more than 90 degrees. So I would say it's on the order of 110, 120. So that's quite often the angle between the two B pyramids. So I got a pyramid on top, and there is like a plane that separates this pyramid from this on the bottom. You can see here the two faces that are in section. So I can rotate it. Perhaps you can see a face, quite evident face here that is quite shiny, and it's a triangular face. So the fact that it's triangular is suggesting that this is part of a pyramid. And so at the bottom you can see here again another triangular face. Is partly included in this matrix, but still that's enough really to recognize this spinel based on the habit of the mineral. So this will be faces, and if you can see with the end lens cleavage, I think that would be hard, because this is very hard mineral, but yeah, that could be another feature that can be identified. Usually hard minerals will less likely develop cleavage because they tend to fracture like quartz in a conchoidal and irregular fashion. The last test really to demonstrate that this is spinel is to take a tool like a glass plate and test for its hardness. Usually spinel is quite hard, and you can see a clear scratch. So comparable to quartz or even higher, sometimes the spinel can go really high. In fact, it's used as a gemstone quality material. So you can think of varieties such as sapphire. Sapphire will be your gemstone quality spinel, and it's coming in a variety of colors. Sometimes it's really red, and so that variety will be called the ruby variety, or in some other instances it will be deep blue, and that's your sapphire. Okay, so the hardness, it's a key distinguishing factor. One thing I didn't mention is that we can take other minerals and use and scratch essentially one mineral against the other and see if it does a scratch. And you can see clearly that I'm scratching basically with a spinel this other mineral, and yeah, in this case this could be something that fits this. So this is your calcite, and so calcite is much softer than spinel. We are actually on the opposite sides, because if you remember, I said the calcite has a hardness of 3. Okay, so that's your calcite, but this is your spinel, and these are some of the ways in which you can identify it. And definitely is an opaque mineral, or it could be very close to an opaque mineral. It depends really on the composition in this particular case. We are close to other important minerals. This one here has a characteristic greenish color, and it's quite translucent. I have a specimen, I think here I can show you better. So there are a number of varieties of these. Let me see, I think this is a rock, but it does give you the feeling of the different types of so we have it here as well. So before I forget, I think we have to be careful. I think I still have these ones here that I want to discuss, and also this one, and yes, let's work a little bit on these. So these are rocks. These are rocks, but they contain 90% of this rock is essentially olivine. So we mentioned olivine at the beginning of the first lecture, And olivine is you know, a characteristic minerals that is found in ferromagnesium rich assemblages such as basalts. So in this particular example, I just wanted to flag that we have crystals of olivine that are quite translucent. So I would place the olivine in this realm. So I would place it in this group here because of this translucency property. It doesn't always appears as clear as in this specimen. So if you see, I can clearly see a glassy appearance for this crystal. Maybe we have other examples here. So that's also quite glassy. So it looks very similar to quartz, but the greenish color, which is more pistachio-like, it's quite characteristic of the olivine. And yes, if we look at an enlarged version of these small crystals, we can have, you know, different varieties. Really, this is a bit darker, this is a bit lighter, but that's because of the matrix of these rocks. They tend to have different proportions of olivine, and so the color will change. Yeah, it's important to realize that you might find specimens like this that have this characteristic green color, and they are usually quite shiny and glassy as well. And so that's a good way of assessing and identifying olivine. You have to think about the hardness as well with this, but yeah, it's quite characteristic, the color, and specifically for olivine, I think it's a good diagnostic feature. In this case, a rock like this, you would have to magnify the rock. So we will look also at some magnifications of this specimen and discuss a little bit more about olivine. But certainly the hardness is a key feature. So if you take your glass, you should be able to scratch with the glass, with the mineral, the glass, and in fact it does scratch it. You can see probably a tiny scratch there. Maybe I can do here. So you can see clearly a scratch in here. So that's indicating that you have a hardness that is certainly higher than 5.5, and we know that the olivine is certainly close to these other minerals, so the pyroxene and amphibole, which is usually between 5 and 6, but this is usually 6.5. So it's very similar to feldspars as well in terms of hardness. We will do other games in which we will try to identify an order in terms of hardness for the minerals. Yeah, that's coming next. I wanted to really understand translucency firstly, because I think it's a critical property for helping you figuring out different minerals. Some will be like this, so you can see I have somewhat similarity in terms of color, but this is a very soft mineral. So here we're talking about serpentine. So serpentine, if you remember, is quite fibrous, so I can actually easily break fibers of this mineral, and you can see here a vein that has this characteristic marks that indicates fibril intergrowth, basically, of this chrysotile. And so this is an example of serpentine. See how I can actually break these small pieces of or flakes of crystals, which indicates that the hardness of this mineral is very low. And in fact, this is comparable, you know, to calcite, or actually even less than that. So we go down to gypsum and also talc. So talc and gypsum and serpentine usually are quite low. And you can see that because even if I use my fingernail, I'll be able to scratch this mineral off of its rock, which is a serpentinite. So remember, this is a rock, but it does contain a good amount of these greenish plugs of mineral, which are your serpentine. Serpentine is also quite greasy. Quite often it feels greasy and soapy, and that's another diagnostic feature, really. So remember, this is usually a product of alterations of rock like this. So if I have a basalt, I can alter the basalt with hydrothermal fluids or through weathering, and I can essentially produce serpentinites. So quite often in mid-oceanic ridges, you will find a sequence of serpentinites, which are the results of peridotite alteration. And so that's another really interesting mineral which gets close to the olivines in color, but the key distinction will be the hardness. So let's move to another soft mineral, and so this is your chalk, and so if you test it with the acid, it doesn't fizz, so calcium sulfate, and quite often you can scratch it with your fingernail. So this will be relatively soft and comparable to this other mineral, which is also gypsum, but you know, in this case this is more massive. Instead, this is well crystallized and has developed characteristic habit, and so in this particular mineral you can also recognize a classical cleavage. So I can see at least 2 cleavages in this particular specimen, actually 3 cleavages to be fair. And again, in this particular case, I would test with acid because this is very similar to calcite, so it's quite soft as well, even softer than calcite. So in this case, you will be able to recognize gypsum because you can scratch it easily with a copper coin. So I made a big scratch here, another big scratch here, and so calcite not easy to scratch with a copper coin. So key distinction really here in terms of recognizing this mineral and comparing it against the calcite. And why am I saying this? Because if I take these, I could easily find that they have a similar habit. So similar habit. So you can see the angle between the faces is kind of similar, so it could be misleading, although it's different, the habit, because I don't get the same type of shift. There is a little bit, but yeah, I think in this case it's much easier to look at things like the reaction with the acid and the hardness to clearly tell apart the different minerals. And yes, maybe we'll discuss that during, or it could be a question for you during your examination. Okay, I think we are, so remember this is chalk, a variety of calcium sulfate. Usually chalk is used, you know, to write on a board, and it's essentially a variety of gypsum. So again, very soft, non-reactive to acid. Other minerals that goes into the family of opaque minerals is this one. One big distinction is also these minerals quite heavy. So you will feel that they are heavy, and that's because of the density. They usually are made up of transition metals like iron, or let's say copper, or like in this particular case, sphalerite is composed of zinc, so it's a zinc sulfide which has some degree of substitution, so you can have also iron going into the structure of sphalerite. Sphalerite is distinguished by the adamantine aspect, so it's very shiny. You can see how it shines here really well, and it's non-translucent, so that's also an important property. The streak is usually a good way to tell things with these minerals. So you can see characteristic yellow to whitish streak. I think that's another important way of telling that this is not, you know, your hematite or magnetite. You can see a yellowish streak, which is quite helpful in the identification of sphalerite. Sometimes the variety of sphalerite will have substitution that makes the sphalerite quite translucent, and in fact it's called honey sphalerite because it is yellow, dark yellow in color, and it will essentially help you as well with the identification of sphalerite because of the characteristic honey color. So it looks pretty much like amber, which is fossilized resin from trees. The famous one are from the Baltic Sea. There were ancient forests that essentially got preserved, and some of the amber comes from the Baltic Sea and has that characteristic honey color, which is very similar to sphalerite. But sphalerite has a completely different composition. This is a zinc sulfide, and so it's going to be classified as an opaque mineral with other sulfides like pyrrhotite or pyrrhot or chalcopyrrhot, or even galena, which we were looking at before. So that's another sulfide. So here we have another specimen which is hematite. So that's another variety of hematite. And then we have sulfur, which we could put here because of the relationship with sulfides. So you can see this lemony yellow color, so light yellow. That's quite characteristic of the sulfur. So this is the one that form on geysers. We saw that when we were talking about volcanoes and the different types of volcanism. So if you remember, we were looking at pictures of the Strombolian island, so where the volcano Stromboli is found, and also the Vulcano island, so where Vulcano is found, and we discussed that some of the venting of gases tend to deposit concretions of sulfur, pure sulfur, and so sulfur will appear with this characteristic crusts, and also has good translucency, adamantine luster, and will have little tiny crystals quite often forming. So in this case, magnification will be helpful. And another way of testing for sulfur is really to use the streak plate as well. You will see a yellow to white streak, which is very similar to what you have for the sphalerite. So another sulfur compound here, but this is of course pure sulfur. So in terms of hardness, let's see if the hardness can be critical. So we test it and we see it's not really scratching the glass. So I would say that the hardness is definitely less than 5.5. And then I would test, with the copper coin that is 3, and see if I can scratch it. And it looks like I can definitely scratch some of the sulfur, so it's less than 3. And then I would use my finger and see if I can break the sulfur away. And yeah, it seems I can actually. So it's, you know, on the order of gypsum, but I would say a little bit stronger. So on the order of 2.5 would be my guess here. Okay, so we have discussed those. Here is another piece of the pyrrhotite. So let's see if I am right. So we should be able to attach a magnet, and you can see it does attach. It does have that bronze color. So definitely I would put it close to this other specimen.